Hi, this class will introduce you to Python design patterns and in particular about creational design patterns. This is the first part of the tri-part video series on design patterns. Even though this is an advanced topic, we will try to cover the topics in detail, so you should be able to understand even if you are new to Python. Design patterns in Python, as in other programming languages, are general reusable solutions to common problems in software design. They provide a template for how to solve a problem in different situations and can improve code readability, reusability, and maintainability. So, what are templates? We all have used templates in various contexts like Word documents, PowerPoint presentations, web development, coding and software development, emails, forms, and surveys. So, a template is a predefined or pre structured format that serves as a starting point for creating something. It provides a framework or blueprint that can be customized or filled with specific details. Templates help save time and maintain consistency. Design patterns in Python can be broadly classified into creational, structural, and behavioral patterns. Let's try to get an overview of these three categories of design patterns. So as you can see, we have creational design patterns which encapsulate object creation. So these patterns encapsulate the process of object creation, making the system more independent of how its objects are created, composed, and represented. So by controlling the object creation, these patterns allow the system to be more flexible and able to change or reuse parts of the system more efficiently. They help decouple the code that creates objects from the code that uses them, leading to more maintainable and scalable code. Now let's look at structural patterns. So they define how objects and classes are composed to build larger, more flexible and efficient structures. They address the relationships between entities and how they interact or are interconnected. These patterns provide guidelines on how to arrange or structure the components of a system. Often they help separate abstraction from implementation, allowing both to vary independently. Let's look at behavioral patterns. So these are primarily concerned with how objects and classes interact with each other. They dictate how objects communicate, cooperate, and exchange information to achieve specific behaviors in a system. These patterns help in organizing the responsibilities among different objects and classes. They define which objects is responsible for a particular task and how that task is carried out within the broader system. So it's a little difficult to understand these concepts without looking at code and specific examples and use cases. Today we are going to cover creational design patterns in detail. Structural and behavioral patterns will be covered in subsequent lectures as part of this tri-part series on design patterns. So let's try to understand the creational design patterns in detail. We will be covering 5 common creational design patterns, and these are Singleton pattern, the factory method, the abstract factory method, the builder pattern, and prototype pattern. So let's start with the Singleton pattern. So this ensures that a class has only one instance and provides a global point of access to it. So when you need to control the access to shared resources like a configuration object or a connection pool, you can use the Singleton pattern. The factory method defines an interface for creating an object, but lets subclasses alter the type of objects that will be created. So we use this when the exact type of object that needs to be created isn't known until runtime. The abstract factory pattern provides an interface for creating families of related or dependent objects without specifying their concrete classes. So you use this when you need to create a group of related objects that belong to the same family. And the builder pattern separates the construction of a complex object from its representation, allowing the same construction process to create different representations. So when you need to construct a complex object step by step and you want control over the construction process, you can use the builder pattern. The prototype pattern creates new objects by copying an existing object, that is the prototype, which can be cloned. So we use this when object creation is costly and you want to avoid creating objects from scratch. Now let's look at the creational design patterns in detail. We will start with the singleton pattern. The singleton pattern ensures that a class has only one instance and provides a global point of access to it. The term global point of access generally refers to a single centralized way to access a resource or service across an entire application or system. So there are four methods to implement singleton pattern, and we will be looking at all four of these methods. So the very first method that we will look at is how to implement a singleton pattern using a class variable. So the singleton pattern, as you can see here, has a class level attribute called this underscore instance. Initially this is set to none. This attribute will hold the single instance of the class. So this underscore instance variable is used to indicate that the variable is intended for internal use within a class or module. That is, this is a private variable, and by convention this is defined before the new or the init functions. As you can see, it's defined before the new function. The new method is a special method in Python responsible for creating a new instance of a class. It's part of the object creation process and is called before the init method. So while init, which is like a constructor, initializes the instance, the new is responsible for actually creating it. So let's try to understand how new works. So typically you don't need to override the new method unless you are working with immutable types like tuples, strings, or numbers, or when you want to control the instance creation process. Example, when we want to implement singleton patterns, as we're doing here. So you can see this, the signature of this function here. So the very first parameter, the CLS, this is the class of which an instance is being created. And of course the other arguments, the asterisk args and the asterisk keyword arguments, these are the additional arguments that might be passed to the init method. Now this CLS is a reference to the class itself, not an instance of the class. So it is used to manage class level attributes and methods. When you look at this condition here, if not CLS instance, so this checks if this underscore instance is none, only then we will create an instance. If the instance is already existing, it will return the instance. It will not create it. So that is what this is checking here. So whether a new instance was created or not, this CLS underscore instance is going to return the existing or the newly created instance. So if you look at here, there are still a lot of concepts here. When you look at this super, so why are we using the super method here? So let's try to understand that. Why should we use super? So as we saw here, the new method is responsible for actually creating a new instance of the class. So when you call super, you're invoking the new method of the parent class, usually object if there's no parent class. This is necessary because the new method in object is what allocates memory for the new instance and sets up the basic structure of the object in memory. Now, if your singleton class is part of an inheritance hierarchy, calling super ensures that the instance is properly created according to the logic of the parent classes. For example, if singleton inherits from another class and that parent class has its own new method with some specific logic, super ensures that this logic is executed, maintaining the integrity of the inheritance chain. So this could be having a parent class. So we need a method like this. We need to call the super so that we don't break the we have to call the the new method of the parent class also, in order not to break the hierarchy chain. So using super makes your singleton implementation more flexible and compatible with potential future changes. If the class hierarchy changes, or if singleton starts inheriting from a different class with a more complex new method, the super will adapt to these changes, ensuring that the correct new method is always called. So by using super, you avoid hard coding the parent class. If the base class changes, or if the singleton becomes part of a different inheritance chain, super will automatically uh, handle the method resolution, ensuring the correct new method is always called. So what happens if we don't call the super? We can instantiate it without using the super also. So if you don't use super and instead directly call object, the new method of the object, you bypass any custom new methods in parent classes. This could lead to issues if those methods are doing something important, like initializing certain attributes or ensuring proper object construction. So using super in the new method of the singleton pattern ensures that the instance is correctly created according to the class's inheritance hierarchy. It provides flexibility, maintains compatibility with future changes, and ensures that any important logic in parent classes is not bypassed. If the parent chain involves more than two parent levels, the super function will still work correctly, ensuring that the new, or any method for that matter, of each class in the hierarchy is called in the correct order. This process is also known as method resolution order, MRO, in Python. So here you can see we are creating creating two instances of this singleton class. But when you look at the statement here, it will it will print you uh, we can see that both of them are pointing to the same object. So here both the instances singleton 1 and singleton 2 are created by calling the singleton class. So the is operator checks if both variables point to the same object in memory. Since the singleton pattern ensures only one instance of the class is created, both singleton 1 and singleton 2 refer to the same object, so making this comparison true. So the singleton pattern ensures that only one instance of a class is created, even if the class is instantiated multiple times. So in this code, you can see singleton 1 and singleton 2 both reference the same instance of the singleton class because of the logic in this new method. That is why singleton 1 is singleton 2 evaluates to true, indicating both variables point to the same exact object in memory. Let's now explore how to implement this singleton pattern using a decorator. So you can also use a decorator to turn any class into a singleton. The decorator pattern will be covered in detail as part of the structural pattern in the following video, but we will explore it here, and we will also see how we can use the singleton pattern, how we can build the singleton pattern using the decorator. First, we must understand what a decorator is and how it is used. So a decorator adds behavior to an object dynamically. You can think of a decorator as some special instruction that adds extra functionality to a function without altering its code. You can think of it as attaching different types of lens to a basic camera to take different types of photos, like zoomed in photos or wide angle views or close-up shots. So each lens adds a new capabilities to the camera without changing the camera itself. So in Python, a decorator is like one of those lenses. Let's try to understand how a decorator is implemented in Python, and we'll try to explain it in simple words because this will be covered much later in the second video. So we start with a function. First, you have a function that does something specific. For example, it might print a message or calculate a value or fetch some data. Then we create a wrapper function. So you create another function, and let's call it wrapper, that adds something extra before or after the original function. This wrapper function is like a middleman. It controls when and how the original function is called. Now, inside the wrapper, you will still call the original function so that it performs its usual task. But because it's inside the wrapper, you can also do additional things before or after the function call, like logging, checking conditions, or modifying the result. So instead of returning the original function, you return the wrapper function. This means that whenever someone calls the original function, they are actually calling the wrapper, which adds extra behavior that you have implemented. Finally, you attach the wrapper to the original function using the @ symbol, as we are doing here. This tells Python that whenever this function is called, use the decorated version with the extra behavior. So in essence, implementing a decorator involves creating a new function that wraps around an existing one, adds some additional behavior, and then reassigns the original function to the new wrapped version. This way, the original function still works as intended, but now with some extra features tacked on automatically. The add symbol in Python is used as syntactic sugar for applying a decorator to a function or a method. It makes the code more readable and concise. So when you place the add decorator uh, name above a function or a class, it tells Python to pass that function to the decorator immediately. The decorator then returns a new function, often wrapped version of the original function, which replaces the original one. So when you place that add decorator name above a class definition, it tells Python to pass the class itself to the decorator function. The decorator can then modify the class or return a new class, which will be used in place of the original one. Now that we understand what a decorator is, let's see how it has been used to enforce the singleton pattern. So as you can see here, the singleton pattern is a decorator. The singleton function, is a decorator that ensures only one instance of a class is created. It contains a dictionary of instances that will store instances of classes it decorates. So we have an inner function here defined inside this singleton function. So this inner function get instance. So inside the singleton function, the get instance function is defined. This function takes any arguments that the class constructor in it might need. The first thing it does is check if the class CLS already exists. If it exists, it's part of the instances dictionary. It's part of this dictionary. If the class is not in instances, it creates an instance of the class using the CLS and the arguments or the keyword arguments that was passed to it, and stores it in the dictionary. This is a dictionary, as you can see here. The instance is then returned, ensuring that every time the class is instantiated, the same instance is returned. The singleton function returns the get instance function. So it returns the get instance function, as you can see here. So the singleton function returns the get instance function. This means that whenever the decorator is applied to a class, the get instance function will replace the normal class instantiation behavior. The add singleton decorator is applied to the singleton class. This means that every time singleton is called, it will actually call the get instance function. It will call this get instance function defined in the decorator. So let's execute this code. So now when we are instantiating this, it goes through the get instance function. Since this is the first time singleton is being called in this step, line number 2, an instance is created and stored in the instances dictionary. When singleton 2, this line is called, the same get instance function checks if an instance of singleton already exists in the instances directory, directory. So since it does, it returns an dictionary, Since it does, it returns an existing instance instead of creating a new one. The print statement here, again, as you can see, checks if singleton 1 and singleton 2 are the same instance, and it is, so therefore we get the output as true. So yeah, so let's continue with how to create the singleton pattern using a meta class. So first we need to understand what a meta class is. So in Python, a meta class is a class of a class, meaning it defines how classes behave. Just as classes define how instances of the class behave, meta classes define how the classes themselves behave. You can use meta classes to customize the class creation, modify class attributes, and more. So a class is a blueprint for creating objects, basically, which is a blueprint for creating instances, but a meta class is a blueprint for creating classes. So by default, the meta class for all classes is type. So when you create a class, Python uses type to create the class object. So everything in Python is an object. So in the meta class is type over here. So everything has a type. So defining a meta class. So you can define a meta class by inheriting from type and overriding some of its methods. The most commonly overridden methods are new. So this method controls the creation of the class. It's called before the class is created. And we also have init. This method is called after the class is created. So it is used to modify the class. Meta classes allow you to control class creation in Python. They are defined by inheriting from type. So you can customize class behavior by overriding methods like new and init. So meta classes are useful for enforcing constraints, adding methods, properties, or modifying classes in a consistent manner. Meta classes are an advanced feature in Python and are typically used in more complex frameworks or libraries where class customization is needed at a higher level. With this basic understanding of a meta class, let's see how we can implement a singleton pattern using the meta class. This approach is more advanced and leverages Python's meta class mechanism to ensure that only one instance of a class is created, even if the class is instantiated multiple times. So this singleton meta is defined as a meta class inheriting from type. In Python, a meta class is a class of a class that defines how classes behave. So this underscore instances is a class level dictionary that stores instances of classes using the meta class. So the call method is a special method in Python that gets invoked when an object is called like a function. For classes, this happens when you try to create an instance. Example, in this case, when you try to create the singleton class. The CLS here, this represents the class being instantiated. So again, here we have this condition which checks if the class is not in this underscore instances, uh, dictionary, uh, it means the class hasn't been instantiated yet. So if the class is not in this instances dictionary, then we will call the super method to create new instances of the class. So this calls the call method of the super class, which eventually calls new and init to create and initialize the object. So the newly created instance is stored in the underscore instances dictionary with the class itself as the key. So whether a new instance was created or not, the instances from this the underscore instances is returned. The singleton class uses singleton meta as its meta class. As you can see, it's defined here as its meta class by specifying this meta class is equal to singleton meta. This means that any time you try to create an instance of singleton, the call method of singleton will be invoked. So here again we have two instances. As you can see, when we are running this code, we are trying to instantiate it twice, but it points to the same object. So the meta class singleton meta controls the instantiation process of any class that uses it. The key logic is in the call method, which checks if an instance of the class already exists. If it does, the existing instance is returned. Otherwise, a new instance is created and stored. So this underscore instances dictionary acts as a cache for instances, ensuring that only one instance of each class using this meta class is ever created. So this implementation of the singleton pattern using a meta class is more flexible and can be reused across multiple classes. The singleton meta class ensures that any class using it will have a single instance, even if instantiated multiple times. That is why Singleton 1 and Singleton 2 evaluates to true. And the reason we use this dictionary here and not just a a variable is that for different classes, like for example our Singleton class, this same code can be used for creating different types of classes. For example, we can have some other class like we have a Singleton class here, and it will still work because as we said here, these classes will be stored as the in the dictionary, and the keys are the classes itself, and the value is the instance that gets created. So this architecture scales. Now let's try to explore the Singleton class using a module. So this is the fourth method of creating a Singleton class. So in this example, the Singleton pattern is implemented using a module level approach in Python. So we will be looking at creating a Singleton pattern using a module now. So in this example, the Singleton pattern is implemented using a module level approach in Python. So the Singleton class is defined within the Singleton module.py file. So you can see this is the Python file that will get written once we execute this cell. So this is a magic command for the Jupyter notebook, which basically just says write file. So I'm going to get this file created in the current directory, and the Singleton class is defined within the Singleton module.py file. This class has an init method that initializes the instance variable to none. So initially we are setting this value to none. A single instance of the Singleton class is created and assigned to the variable Singleton. So this is our variable. This instance is at the module level, making it accessible to any code that imports this module. So the Singleton module is imported in the main.py file, which we are doing here. We are importing this module. Two variables, Singleton1 and Singleton2, are assigned the value of Singleton module.singleton. Since this Singleton module.singleton refers to the same instance created in Singleton module.py file, both Singleton1 and Singleton2 will point to the same very object. So as you can see here, this therefore returns true. So the print statement returns true because it's referring to the same object in memory. So in Python, when a module is imported, its code is executed and the module level variables and functions are created and stored in memory. The Singleton instance is created when Singleton underscore module is first imported here, so it gets created. Python's import mechanisms ensures that a module is only loaded and executed once per interpreter session. Subsequent imports of the same module do not re-execute the module, but instead provide access to the already loaded module's namespace. This means that every time Singleton module.singleton is accessed, every time this is accessed, it refers to the same instance of the Singleton class created during the module's initial import. So they point to the same object in memory, as we can see here. So in this approach, the Singleton pattern is implemented at the module level, where a single instance of a class is created and shared across the entire application via module imports. So Python ensures that the same instance of the Singleton class is used, effectively creating a Singleton. So that is why Singleton1 and Singleton2 return true over here. Now let's move to another category of creational design patterns, which is namely the factory method pattern. Now in this approach, we define an interface for creating an object, but we let the subclasses alter the type of objects that will be created. So we use this when the exact type of object that we need is not known until runtime. So an example of this could be creating different types of user notifications, for example email or SMS, based on the user preferences without changing the client code. So it creates objects without specifying the exact class of object that will be created. The factory pattern is a creational design pattern that provides an interface for creating objects in a superclass, but allows subclasses to alter the type of objects that will be created. It's useful when you need to create objects that can vary based on user input or configuration or some other conditions. So looking at our example, so we have an animal class which acts as an abstract base class. So this is a base class, and it defines a method speak, which is not implemented. You can see we just have this code here. So we are using pass. There is no implementation for this. The idea is that this method will be overridden by the subclass. So we have this dog and cat, which are the concrete implementations. So dog and cat are subclasses of animal. You can see they both have animal as the parent class. They each override the speak method. They both have a speak method, which they override to provide specific behavior. So as you can see here, we are returning different, different values here. So these classes represent specific types of animals and their corresponding sounds. Now, this animal factory class, this is a factory class with a static method get animal. So this is a static method which is defined here. It's a decorator. This method takes an argument animal underscore type, which determines which type of animal object to create. Now, if this animal type is dog, then a dog object is created. If it's a cat, then a cat object is created. And if it does not match any known class, then none is returned. So what exactly is this static method? So the, the get animal method is marked as a static method, meaning it can be called without creating an instance of animal factory. So it's like it becomes a class method. We don't need an instance of this animal factory. So the animal factory dot get animal is called, which returns a dog object, and when we use it with cat, it returns a cat object. So let's run this code, and you can see that it prints correctly. So we are using this simple factory method, and we are creating instances of derived classes which are determined only at runtime according to the value that is being passed to this get animal method. So this helps in the client code being decoupled. So uh, from the specific classes, whether it's a dog or a cat. So now let's look at the abstract factory pattern. So this provides an interface for creating families of related or dependent objects without specifying their concrete classes. So we use this pattern when we need to create a group of related objects that belong to the same family. So we are going to look at this abstract factory method. This is an extension where the factory method is part of a base class and can be overridden by subclasses to provide more specific object creation logic. So a typical example for this would be in the real world, it could be like designing a UI framework that can generate different types of UI elements, whether it's buttons or text fields for different platforms, say Windows or Mac, while keeping the code base independent of platform specifics. So the factory method pattern is an extension where the factory method is part of a base class and can be overridden by subclasses to provide more specific object creation logic. So let's look at this ABC module. So the abstract base class module provides the infrastructure for defining abstract base classes in Python. An abstract base class is a class that cannot be instantiated on its own and is designed to be a base class for other classes. It may contain one or more abstract methods, which are methods that can have a declaration but no implementation, as we have over here. There is no implementation for this. So this code demonstrates the use of the ABC module to implement the factory method design pattern. The factory method pattern is a creational design pattern that provides an interface for creating objects but allows subclasses to alter the type of objects that will be created. So here animal is a base class that cannot be instantiated directly. It defines an abstract method. As we said before, it defines an abstract method speak that must be implemented by any subclass that inherits from animal. So we have these concrete subclasses, dog and cat, which again they are, animal is the parent class. Both classes implement the speak method, So there is a implementation for the speak method in both these classes. Now we have an abstract factory class. So this is another abstract base class. So it defines an abstract method. So there is an abstract method again over here, just like we had over here, which says create animal, that must be implemented again by it must be implemented by the uh, subclasses. So the purpose of this method is to create and return an instance of an animal subclass. So why do we need this? Why do we need this dog factory and this cat factory classes? So the dog factory and cat factory are concrete subclasses of animal factory. These factories are responsible for creating specific types of animals without specifying the exact class of the object that will be created, as you can see here. So in this example, an instance of dog factory is created. So we are creating an instance of this dog factory here. The create animal method. So the create animal method, as you can see here, um, here, the create animal method of dog factory is called, which returns a dog object. So we are returning a dog object. So when the speak method of the dog object is called, it prints the correct, um, it prints the correct values, as you can see here. So let me execute this code till here before we go ahead. So you can see we are getting the correct output. So the abstract base class animal factory provides a template for creating animals, but the actual creation process is handled by subclasses like dog factory and this cat factory. This pattern is useful when the creation process is complex or when you want to delegate the responsibility of creating objects to subclasses. It allows the code to be more flexible and extensible, as new animal types can be added by simply creating new factory classes without changing the existing code. So why do we need this dog factory and this dog factory and the cat factory and animal factory classes when we have this dog, cat and animal classes defined here? So the use of these factory classes in the code example is related to the factory method design pattern. This pattern provides a way to encapsulate the object creation process, allowing for greater flexibility and extensibility and decoupling the client code from specific implementations. So the factory classes encapsulate the object creation process. Instead of instantiating objects directly with dog and cat, the creation is done through a method. So we are using this method here, create animal. This allows for more control over how objects are created, including managing dependencies, setting initial states, or implementing caching mechanisms. So we can control how the objects get created. So this helps in decoupling of code. Um, by using these factories, the client code, that is the code that uses the animal objects, is decoupled from the specific classes, dog or cat. The client interacts with the factory rather than directly with the classes, which makes it easier to switch out implementations without changing the client code. For example, if you want to create a new type of animal, say a bird, you could simply add a bird factory without changing the code that uses the factory. So this handles complex creation logics. So for example, if a dog object required several parameters or needed to be created in a specific state, the dog factory could handle all the complexity internally. This also supports dependency injection, which is an advanced topic. We can look at it later. Uh, and it also helps in managing object life cycles. So factories can also be used to manage the life cycle of objects, such as implementing singleton patterns, pooling objects, or managing object reuse. So this can be useful in scenarios where object creation is expensive and you want to control how and when objects are instantiated. So the dog factory, the cat factory, and animal factory classes add flexibility and maintainability by abstracting the creation process. This is especially useful in larger systems where the creation logic is complex or you want to decouple the client code from specific implementations. However, in simpler scenarios, directly using the cat, dog, and animal classes without factories might be sufficient, as we have done it in this simple factory method over here. So um, so now we come to the builder pattern. Let's explore this builder pattern here. So now we're going to explore the builder pattern. So the builder pattern separates the construction of a complex object from its representation, allowing the same construction process to create different representations. We use this when we need to construct a complex object step by step and you want to have control over the construction process. So this separates the construction of a complex object from its representation so that the same construction process can create different representations. It helps in creating objects with many optional components. So for example, if we want to construct a complex object like a pizza, where you want to specify various toppings, sizes and crust types without requiring a large number of constructor parameters. So this separates the construction of the complex object, in our case the pizza, and from its representation so that the same construction process can create different representations. So we can add our toppings as and when we choose to. This pattern is especially useful when an object has multiple optional fields or requires complex setup. So as you can see here, we have the class product. This is the complex object that is being built. We have this product builder, which is a class that constructs the product by adding paths to it. So we have defined the paths here, which is right now an empty list, and the product builder has methods. We have this builder methods like build part A and build part B here. Each method in the builder is responsible for adding a specific part to the product. This method returns self. These methods are returning self, enabling the chaining of method calls. This provides a fluent interface. Finally, we have this get product. This method finalizes and returns the constructed object. So this example demonstrates how the builder pattern can be used to construct a product with various parts in a flexible way. We are chaining the parts that we want to build, and then finally calling the get product, which returns us the product. As you can see here, let's run this, and you can see the output here. We have this product is made up of these components. So now we come to the prototype pattern, and let's explore the prototype pattern. So the prototype pattern creates new objects by copying an existing object, the prototype, which can be cloned. So we use this when an object creation is the object creation is costly and you want to avoid creating objects from scratch. So it is typically implemented by creating a base class with a clone method. So we have a clone method here that duplicates objects. So the prototype class that you see here, this has a clone method that returns a deep copy of the object using copy.deep copy method. This ensures that all nested objects are also copied. We have a car class here, which this class represents the specific type of object that can be cloned. It inherits from prototype, which is defined here. So we are creating a prototype instance by creating an instance of this car class. A new car object is created by cloning an existing prototype car object. So now we are using this. We are creating this cloned car by using this prototype car object. So we are using this prototype car and doing a clone. We are doing the cloning of that. The cloned object, which is this one now, can then be modified independently of the original prototype. So in our case, we can change the color and we can add some options like a sunroof. So it can be modified independently of the original object. So let's execute this. And you can see our cloned car is having the extra, um, it has been modified and it has this sunroof. So it has its own, um, so it has been created using the clone method, but we can modify it. So in this tutorial, we have covered the creational patterns. We looked at singleton pattern showcasing 4 methods to implement it. Then we looked at the factory, abstract factory, builder and prototype patterns. In the next video series, we will cover structural and behavioral patterns. So thank you everyone. All the best.